Hi, in this video I will talk about solubility and its effect on recrystallization, which is one of the most important techniques that we usually use in an organic chemistry lab to purify solids. Let's start with solubility. Solubility is the maximum amount of solute that can be completely dissolved in a certain amount of solvent at a certain temperature. Solubility is usually measured in moles per liter, grams per liter, grams per milliliter, milligrams per milliliter, or even grams per 100 milliliters. So there are different units to measure the solubility of a compound. What are the factors that affect the solubility of an organic compound? The first one is the properties of solute and solvent, and basically we are talking about the intermolecular forces that exist in the solute and in the solvent. The second factor is temperature. Now, regarding the properties of solutes and solvent, usually we have a rule which says that like dissolves in like. So polar compounds are expected to dissolve in polar solvents, and non-polar compounds are expected to dissolve in non-polar solvents. And this is because usually a compound will dissolve in a solvent which has a similar type of intermolecular forces. For example, NaCl, which is an ionic compound and it is polar of course, dissolves in water, and water is known to be a polar compound, but it doesn't dissolve in pentane, which is a non-polar compound. Why? Because water is polar and NaCl is polar, so they have a similar type of intermolecular forces, and that's why they can dissolve in each other. Wax, which is an organic non-polar compound, is expected to dissolve in pentane, which is nonpolar, but definitely it doesn't dissolve in water. Why? Again, because it's polar. Polar compounds are usually called hydrophilic because they like water, they can dissolve in water, whereas non-polar compounds are called hydrophobic because they don't dissolve in water and they try to avoid it. Solubility of polar compounds. Some organic compounds such as alcohols, amines, halides, and acids have polar and non-polar regions. Usually the functional group of the compound represents the polar side of the molecule, and the carbon chain represents the non-polar side, which is the hydrophobic side. For example, let's say in the case of alcohols, the functional group, which is OH, represents the hydrophilic part of the molecule, and the carbon chain represents the hydrophobic side. The same thing applies for amines, where NH2 is the hydrophilic side, or even carboxylic acids, where the carboxylic acid functional group represents the hydrophilic part and the carbon chain represents the hydrophobic side. Now, the ratio of the size of the non-polar side to the polar side is one of the most important factors that affect the water solubility of these compounds. As this ratio increases, which means as the size of the non-polar side increases, or as the number of carbons in the carbon chain increases, then the solubility of the compound usually decreases. And there is a rule which is called the 4.5 rule. So up to 4.5 carbons, the compound is expected to have some solubility in water, and then after that the solubility will dramatically drop. For example, methanol, which has 1 carbon only, and up to propanol, which has 3 carbons, are completely soluble in water. Now, butanol, which has 4 carbons, is slightly soluble in water. We can only dissolve 7.4 grams in 100 milliliter of water. And then once we add 1 more carbon, pentanol, then the solubility will drop from 7.4 to 2.2 grams per 100 milliliter. And this means that the compound is almost insoluble in water. So to summarize, whenever we have an organic compound which has a polar functional group and a non-polar carbon chain, then increasing the number of carbons in the carbon chain will decrease the solubility of the compound. Up to 4 carbons, the compound is expected to have either complete solubility or high solubility in water. However, once we increase the number of carbons to 5, then the solubility of this compound will drop dramatically in water, and the compound is considered as being insoluble in water. The second factor which affects solubility is the temperature. It is well known that as temperature increases, the solubility of solutes in a solvent will increase. And this is because heating increases the kinetic energy of the solute molecules and the solvent molecules. Now the molecules are moving fast and they are colliding more, and because of these collisions, the energy which is produced from these collisions will break the intermolecular forces. Again, to explain more, so let's say these are the solvent molecules and these are the solute molecules. Now, in order for the dissolving process to take place, the solvent molecules have to surround the solute molecules. And to do this, the first thing we should be doing is breaking the intermolecular forces which keep these molecules together. Now, when we heat the solvent and the solute, those molecules will start moving fast. So the molecules will start moving fast and they will start colliding. This collision will produce energy. The energy is needed to break the intermolecular forces. Now those solute molecules will start to move away from each other, and once they do this, they will be surrounded by solvent molecules. And that's why in general we know that as temperature increases, solubility increases. Now we are going to use the information which I talked about in these two slides to understand an important purification technique which is used in organic chemistry lab, and it is called recrystallization. So what is recrystallization? Recrystallization is a purification technique that is mainly used to purify solids. We do this by dissolving the solids in a hot solvent and then recrystallizing them, leaving the impurities in the solvent. So whenever you have an impure solid in an organic chemistry lab, one of your first choices to purify this solid is by using the recrystallization technique. We will explain the steps of the recrystallization technique in the upcoming slides. For now, usually it is used to separate two compounds, and we will explain this in a minute, or to purify a compound by removing the impurities from this compound. Now, what is this technique based on? It is basically based on these principles. The first thing is that different solutes have different solubilities in the same solvent. For example, let's say we have a solvent which is ethanol, and we have a solid compound called A, and another compound called solid B, and we will see the numbers in the next slide. But for now, just to understand this statement, the amount of A that can be dissolved in ethanol is different than the amount of B that can be dissolved in ethanol. For example, we can, let's say, dissolve 5 grams of A in 1 liter of ethanol, whereas, for example, compound B, we can only dissolve 1 gram per 1 liter of ethanol. So this is what I mean by different solutes have different solubilities in the same solvent. We are going to use this property to separate compounds A and B, as we will see in the upcoming slides. The second thing is that solubility decreases as temperature decreases, and this is what we talked about in the previous slide when I said that solubility increases as temperature increases, or vice versa. And the third principle that makes recrystallization a good separation or purification technique is that molecules of the same compound usually have higher tendency to stick together, to form crystals together, and this is again what makes it a good purification technique. And again, we will explain all these statements in the cases that we will talk about in the upcoming slides. Case 1, separation of two compounds. So how can we use recrystallization to separate two compounds? So the principle is that different solutes have different solubilities in the same solvent. As I said before, let's say we have two compounds, compound A and compound B. The solubility of compound A in ethanol at room temperature is 0.05 grams, which is very low. Whereas the solubility of compound B at the same temperature is 1.5 grams. Now, at 100 degrees, or for example, at the boiling point of ethanol, the solubility of compound A will be 5 grams, whereas the solubility of compound B will be 15 grams. Now, based on this, when I add A and B to ethanol and I heat the compound, both compounds will dissolve first. So both compounds A and B will dissolve first, as we can see here that both A and B now are dissolved in the solvent. Now, once we start cooling the whole solution, the less soluble compound, which is A, as you can see here, so we can only dissolve 0.05 grams of A in ethanol at room temperature. The less soluble compound, which is A, will start to crystallize. So it will come out of the solution and it will form crystals here. The other compound, which is compound B, will stay dissolved in the solvent because it's more soluble. And based on this, upon filtration, using the filtration technique, which we will discuss later on, compound A, which is a solid, will stick to the filter paper, which is found here, and then compound B will go down into this solution, which is now called the filtrate. So the filtrate is the solution which is collected after filtration. And this is how we were able to separate compounds A and B. Again, we were able to separate them because B is highly soluble in the solvent, A is not highly soluble. So upon mixing them both in the same solvent, heating and then cooling, we were able to force A to form crystals again and collect it on the filter paper, whereas B remained in the solution and it was collected in the filtrate. Now, let's say in some cases we have two compounds A and B, and after heating we were able to dissolve one compound but not the other. In this case, there is no need to cool the solution. We can just do something which is called hot filtration. We will talk about later on. So we can easily heat and filter, and then the insoluble compound will remain on the filter paper and the soluble compound will go down. One of the easy examples that I can talk about here, let's say you have a mixture of sugar and sand. The easiest way to separate them is to add water to this mixture and then heat it a little bit. Sugar will dissolve, sand will not dissolve. Once you filtrate, sand will stick to the filter paper, whereas the water and sugar will go down. Later on, you can just evaporate the water solution, and then you can get the sugar. So this is one way of using, it's not recrystallization, this is not recrystallization, but this is one way of separating two compounds using this technique.